So continuing on from the last couple of videos, I'm going to talk about the cumulative distribution function today. And I'm going to jump straight into the definition. So we define this cumulative distribution function as the probability that a random variable is less than or equal to some input value that we pass to the function. And the key thing to note here is that I've actually used a capitalized letter here to denote the cumulative distribution function itself. And this is something quite common where we do use a capitalized letter for writing the cumulative function. And I want to kind of dive into the both cases that we've explored again in the last couple of videos. So if you remember, the first case is actually we looked at the discrete random variable, and we actually went further to use an example of the coin flip, or even better, the unbiased coin flip, and we defined its mass function as the Bernoulli distribution. So I can write that down here, times it by a half to the power of 1 minus x, where the inputs x are defined by the possibilities of a heads or a tails. So a heads is a 0 and a tails is a 1. So let's draw this real quick, the mass function graphically. So it has inputs x, and the y-axis would be the mass function itself. And because it's an unbiased coin, we said that the probability of a heads 0 or a tails 1 is a half. So whatever the case, you get a half, like so. And so what we wanted to do is to define the cumulative mass function. So if I go here and say this is again the probability that the value of the coin flip will be less than or equal to some specified value we pass through. And let's use subscripts here. So I'm gonna have the input be subscripted with the letter n, right? And if we go to the original function definition, let's call this value 0, which is meant to be heads, x0. And this value 1, which is meant to be tails, can be x1. And so you can see how by changing n, we kind of iterate through the different possibilities. So if we chose n as 0, the probability of having a number less than or equal to x0, which is 0, is in fact just a half, because the probability of having something less than or equal to 0, in this case would simply be just the probability of getting a 0, because all the values below 0 have a probability of 0, sorry. And likewise, if we chose n as 1, so we looked at the probability that x was less than or equal to x1, which in this case is 1. We would be looking at the probability that the value of the coin flip would be a 0 or a 1, because 0 is less than or equal to 1, and 1 is also less than or equal to 1. We look at both of these scenarios. So let's write this down a bit. So initially, if n were 0, it would be the probability that x were equal to x0, which is the mass function of 0, which is a half for n is 0. And likewise, if n were 1, it would be the probability that x is x0, or the probability that x is x1. So the probability of a heads or a tails, which is actually the probability of a heads, which was a half, plus a half, which is 1. And this was for n is 1, right? So this is for this specific case, we can see that we've defined the cumulative distribution function, but in the general case, which is what we kind of want to look at, we would actually define this as the sum over all indices of the possibilities. So the sum from I is minus infinity up to n, where again, this letter here would in fact be subscripted by some index n. And we'd sum over all of the probabilities, which are defined by the mass function. So we can say fx of xi, right? So just going over this again, the probability that a random variable, or in general, a random variable x is less than or equal to some value indexed by the letter n would be the sum over all values below that input value of the probabilities for those possibilities. So again, I'm going to put a box around this, and that is the definition for the discrete case. So we can also draw this graphically. So we have a similar graph where the inputs are, in this case, still 0 or 1 for heads and tails, except now that the y-axis will represent the cumulative function, right? And so remember, we saw that for 0 we had the value of a half. So this is still a half if I put a half here. But now at 1 we have this value of 1, right? Because there is 100% probability of observing either a heads or a tails in this scenario. And so what we actually end up with is somewhat of a step function where it jumps, or the function output jumps at 1 up to 1 and then continues on from there. So again, if I picked some value here, let's say this is a half, right? The probability of getting a value less than or equal to a half would be the probability of just getting a 0, because there are no other values below 0 with a probability of greater than 0. And so that's kind of the discrete case. Now let's look at the continuous case, which is the second scenario that we've kind of been exploring. And so if I write this here, continuous. And we have been looking at the example of someone picking a random number between 0 and 1. And we drew the density function for this as a uniform distribution. So here we go, where the number that I'm choosing, x, can be in the range 0 and 1. And let's draw this distribution again. So we have inputs x, and we're trying to model the density. So I can pick any number in this range 0 to 1, and the density of all possibilities is 1, such that the area under the graph is also 1, which essentially is another way of saying that the probabilities of all the possibilities are sum to 1. And so again, we want to look at the cumulative distribution function, which we again have defined as the probability that you choose a number less than some value that we're picking, which in this case, because of the probability density, function, or the nature of the probability density function, is actually just the area of the function or the graph in the range 0 to whatever that number I chose is, because there's no density below 0. So in this case, for example, say I picked a half and I wanted to get the probability that you pick some number less than a half. So you could pick 0.1, 0.2, 0.15, 0.49999. That probability, or the probability of picking any of those numbers is simply the area of this probability density function between technically negative infinity, but in the practical case 0, up to the number that I've chosen, which in this case was a half. And so in this, another way of writing area again is integral. So in this case it would be the integral between 0 and the number that I've chosen, x, of the density function. And again, because we want to kind of show the general case, we can see how this translates to the integral from minus infinity to x of the density function. And again, I'm going to box this. And that is the case for the continuous function. The probability that the value of a random variable x being less than some value we define, which in this case is small letter x, is the integral from negative infinity. So all the possibilities from negative infinity up to x, and the probability of those possibilities. So now that we've kind of gone through that, we can look at some general rules we can infer from this function. So because the probability of all possibilities should sum to 1, then the probability of choosing a value less than or equal to infinity, so all the values from negative infinity up to positive infinity, which by definition should be the entire real range, should be 1, right? So we can say that the cumulative function at infinity should be 1. Furthermore, there should be no possibility of choosing a value less than negative infinity. So we could say that the cumulative distribution at negative infinity should be 0. And furthermore, because probabilities are positive semi-definite, which means that they're greater than or equal to 0, you can't have negative probability, then if I pick two numbers, say x1, which happens to be less than another number x2, then I can also say that the cumulative, or the value of the cumulative function at x1 should be less than or equal to the function at x2. And these are kind of criteria for the cumulative distribution function. And I'll go through this last one a bit more here. So again, because probabilities are always greater than or equal to 0, if the possibility that I've chosen x2, for example, say let's relate this back to the choosing our number between 0 and 1. So I'm going to even draw the cumulative function here too. So because let's say that I pick a value a half, I'll pick the value 0, and if this goes all the way up to 1, but I'll also have a look at the value a half. So because the density and therefore the probability of or actually probabilities are 0 because it's the continuous case. But okay, at least the density is greater than 0 for all possibilities. Then actually, by the integral law, integrating over positive values leads to a continuously increasing function. So the value of the function at a half would be larger than the value at 0 because we've added all of the probabilities in that range. And if we actually drew this function, it would just end up being a straight line, capping off at 1, where this is 1. And in fact, at a half, this would be a half. And yeah, I hope that this has been useful, and I'll see you next time.